Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering the Origin and Models of Ferrite Beads. I'd like to thank Evgeny Smidotsky for his many contributions to this presentation, which actually made it possible. Now, we are given by manufacturer this type of plots for ferrite beads. There's sort of some mystery around it. What we see here is that the total impedance of this bead, this is like the series impedance, is composed of a inductive part. X is omega L, inductive part, and then there is a resistive part. At low frequency it's mainly inductive, and then it becomes resistive. And then they are also providing us with this simple model in which we have fixed elements here, L1, R1, C1, and then R2 in series. This is the DC resistance. This is just a parasitic part, so it has nothing to do with the actual behavior of the ferrite bead. But these elements are actually responsible for sort of emulating or generating this type of behavior. Now, in this presentation, I'm going to discuss, first of all, the question, this ferrite bead, where is it coming from? What's the origin of the ferrite bead behavior? And then I'm going to talk about generic models, which are more basic, not just fitting. This model is just fitting to data that, again, I'm not sure if it's measured or calculated. We'll talk about it in a while. And then the question is, what is the origin of this plot here? And then what is the generic model? That is the one that is really represent the sort of first principle, if you wish, of the information that we are getting about the ferrite. And then what is then the accuracy of these models? Are they good enough or not good enough? Or what are the kind of errors we could expect? So this is the objective of this presentation. So the first point to make is that the origin of the fundamental behavior of a ferrite bead goes back to this plot. This is shown for a ferrite material 3611. This is not exactly the one that is best ferrite for ferrite beads, but this is just an example. I'm going to show other examples. So what we see here is the permeability. This is the relative permeability of the material. Is a function of frequency, and that you see that it's this prime, mu prime, is sort of constant up to here, then it starts dropping, the permeability. On the other hand, we have another component here, the double prime here, which is very low here, and then it goes up with frequency, and then it drops again. Now, what is this thing? Well, it turns out that this is a imaginary permeability. So the total relative permeability of a ferrite material, or ferromagnetic material you might say, is the real part and the imaginary part. This is the imaginary part here. So what is this imaginary part? So let's have a look at the equation for an inductor built around the core of a magnetic path length of L, cross-section area A, and N turns. The expression is L times this constant, I'll call it K, mu sub 0, which is the permeability of air or vacuum, and then this is this relative permeability. Now I'm plugging in this value, and I'm looking at the impedance. Impedance is J omega L. L now is this complex thing here, okay? And so when you multiply it, J and minus, it becomes plus, while this term still retains the imaginary behavior. So we see that the impedance is composed of two parts, an inductive part and a resistive part, very similar to what we are talking about in the ferrite beads. So this is inherent in any ferromagnetic material. This represents the losses. This is another way of looking at losses rather than the Steinmetz equation and some other method. This is altogether a different way with imaginary permeability. Though I can interpret these as a resistor and a inductor. This will be the inductor. J omega is part of the impedance calculation. And these are the expression for the resistive part, and this is the expression for the inductor. And all these are frequency dependent because, first of all, omega here is frequency. Secondly, this is for the value of R, right? And this is the permeability, the imaginary permeability is also frequency dependent, goes up and down. And this is also frequency dependent, the mu prime. So this is the model, but these elements are high order type of frequency dependency, very complex, okay? So now we know that we can translate a series connection of a network here to a parallel one. The problem is, however, that when you do this transformation, even if this would have been a fixed element, not frequency dependent as we have it here, these would be frequency dependent. So for each one of the frequencies, you have different values here. If this would be frequency independent, but they are also dependent. So the whole thing is really very highly frequency dependent. So how do you get this parallel network? Well, one way to do it is to write the admittance here, 1 over z, this here, this is this z here, and then multiply it by this conjugate to get a real number here, real expression here. And then you have two parts here, real and imaginary, and then you express it like 1 over and 1 over, so this is an admittance, and this is a parallel connection of these two. So RP is this expression, and LP is this expression. Now this is again very highly frequency dependent, not because you have an omega here, because LS and RS are frequency dependent as well as here, of course, and here we have also the omega. So this is approaching the model that the manufacturer are giving us for the ferrite beads, but in our case we are getting here something very, very complex. So to study what is going on, we did the following. We took this particular example and sort of digitized it, get the numbers here, and then fitted it to a polynomial. And what we are seeing here, this broken part here, the digitized version, not very accurate as you can see, and then the smooth curves are the fitting. So we got a fitting to these two lines that we can walk with, and this of course fitting is a function of frequency, okay? So we get a fitting to this and a fitting to this. Now we can actually look at the impedances. So we looked at the impedance of the parallel and series models. That is, we have the two models with the transformation in between. And just a sanity check here, we see that we get, if transformation is correct, exactly the same impedance. Okay, this is the impedance of the whole thing, end to end. Once it's in series connection, one in parallel connection. And here they are broken into the inductive and resistive part. So what we see already is something that starts to look like what we have seen earlier, in that we have the inductive part like this. This is like a fixed inductor because it goes up with frequency, the impedance, but then it goes down, so this is highly non-linear, of course, and then we have a resistor which is changing with frequency, the resistance, and then also starting to drop. So this is what we got from this, okay? This is the measured complex permeability of this ferrite. If we look at the phase of this impedance, we see here inductive. Well, there's a question of sign here. The question is what is the polarity of the excitation, but this is inductive here, 90 degree, and then it goes down to be resistive, as you would expect, because in this region the resistive part, this one here, is dominant, is the highest one, so therefore the contribution of the inductor is low and it doesn't add much phase shift, and we see primarily the resistive part. So this explains this very nice. These are, again, the two models of series and parallel, non-linear, based on the data of the complex permeability. And here it is. This is the complex permeability. This is now the behavior of the impedances for a given K, right? That's actually K is 1 here, I think. And you see already that it's getting very close here. And that is, you have the inductive behavior here. This is the inductive. And then you have the resistive behavior. This is the resistive behavior. So, well, the break here is farther away, but in general, of course, the material is different. It's a different material for this ferrite bead than this one. And so you're not expect them to be exactly the same, but the behavior looks very good. But this is obtained with a model which is highly non-linear, not fixed element. So how come that you get this with this fixed element? This is the question here. And then all of a sudden we got here a capacitor. Well, we didn't have any capacitor here. Everything was like inductive or resistive. And here all of a sudden we have a capacitor. So let's probe into this. To do this, let's look at this equivalent circuit. This is the simple equivalent circuit of the ferrite. It's a given ferrite from the data sheet, one ferrite. And we can observe the following. When it comes to the parallel section, the impedance of this parallel section will be mainly dependent on the impedance which is the smallest one. If the impedance of the inductor is the smallest one, then in parallel with these ones which are larger, it's basically this one. So whoever is the smallest one wins here, and the impedance will be according to the smallest one. When it comes to the series connection, the largest one wins, because then if the impedance here is very high compared to 0.3, then obviously the 0.3 doesn't matter. And on the other hand, at very, very low frequency, or relatively low frequency, the impedance of an inductor is very low, and it definitely could be lower than 0.3. So 0.3 will be the impedance that you will see here overall. So parallel is governed by the smallest impedance, and the series by the largest. So here is what I did. I plotted the impedances of each one of these. For the resistor, it's a straight line. This is R here, and RS here, a straight line. But for the inductor and capacitor, they are of course frequency dependent. The capacitor, impedance of the capacitor goes down. This is that log-log scale, so it's a straight line. And the impedance of the inductor is going up. So going back to this rule of thumb that I just gave, looking at this parallel section, here for example, the smallest one wins. This is the inductor. So the inductor wins here. So we see this behavior. When it comes above this point, you see that the impedance of the capacitor is the smallest one, so the capacitor wins. And this is actually creating this shape. So the idea is apparently that you got this shape, and then you find an inductor for this part and a capacitor for this part. This is artificial. There is no capacitor to begin with, but you use this capacitor to get this drop, because otherwise you will not get this drop with fixed resistors. Now also notice that at low frequency here, the impedance of the inductor is below RS. Okay, so RS wins because they are in series. This is RS is larger, and indeed you see here a straight line. So this shape is explained by these fixed elements, each one working in its own range. So that if you have a shape something like of this nature, then you can do a fitting so it will sort of fit to the shape that you had at the beginning. Now the vendors are actually giving a simple model. This is this one. This is just a replica of this simple model and just plotted in a, not in a sub-circuit. This is a sub-circuit and this is just a lumped element. But then they give also a precise model. Now what is a precise model? See, this is the simple model. This is the L and the two R's and C1 and L1. This is the simple model we talked about. The precise model is a sort of a ladder type model. It has many inductors and resistors and more capacitors. So it's sort of a better fit to the waveform, but still it has capacitor for the drop. There's no question about that. Now if I compare now these one to the other of same ferrite bead, of course, now these two are exactly the same because this is the sub-circuit and this is the lump circuit, so it's the same. But this is the precise, so it's not exactly the same. But now looking at the phase, so the phase first of all shows the inductive behavior and then it goes down to be resistive as you would expect. But this is up to the peak here. This is just about the peak here. We don't see the drop. Now what happens when you have a drop? So here is a case in which we have a bead in which data is given for this part here beyond the peak. So we see the impedance, we see the resistive part, and then we see the inductive part. Now look at this. The inductive part at this point becomes negative. Well, what does it mean? It means that it is capacitive. It's 1 over J. So we see that the model itself indicates that you have here a negative phase. Again, this is not native to the basic information of the ferromagnetic material. This is something which is artificial, this phase shift. So in this range, the bead behaves as a capacitor and not an inductor as it should be according to the data of the complex permeability. And here I sort of ran it LT-SPICE, the model, this one, compare it to here. Well, the impedance is very nice, but if I look at the phase, clearly from this point it's capacitive. Well, they don't show the phase. Well, I guess they understand that there is a problem here. Probably they don't want to emphasize this problem because this is probably incorrect, the capacitive behavior here. Now, this model is for this particular bead, and these are the values. This is the DC resistance. See, the capacitance here is 0.28 of a picofarad. The question is this the package or is this an added capacitor to the model? Apparently it's added because we have other numbers too, like 0.6. And also, if I look at the capacitance of, well, I got only a resistor, it's film resistor, and this is the same package that we are talking about here, and you see that the capacitance of this resistor is 0.02. So this is probably approximately the capacitance of the package. But see here, there is a model here of a ferrite bead with the capacitance which is even lower than that. This I don't understand. Because if the measurements are made on a package, then they should see probably a somewhat larger capacitance. So the question is, the model obtained by measurement, or is it just actually starting with the complex permeability and fitting it to this simple model? Well, I don't know. I have no idea. The only thing I can say is that the capacitor is sort of artificial, just for the fitting, and the phase that it is adding is probably incorrect, and therefore the information that the model gives us of frequencies above the peak are probably incorrect in terms of the phase, meaning that it's not an inductor, it is a capacitor. So let me summarize what we have seen here. The main point is that the origin of the ferrite bead behavior is coming from this concept of complex permeability, which is obtained, I guess, by a measurement. And then the complex permeability is actually resulting in an LR in series. Okay? Now these can be transformed into a parallel network, but the elements of this network are highly frequency dependent. On the other hand, the simple parallel model given by the manufacturer is with fixed elements, so it's an approximation, and the fixed capacitor is apparently used to get a better fit at frequency beyond the peak. It's not clear if the capacitor is also reflects some of the parasitic capacitance of the physical bits. It's not clear at all. But the bottom line and my conclusion here is that the phase of the simple parallel model is probably in error for frequencies beyond the peak of the impedance. Okay? So if you have to worry about this region, or if it's useful to you, then be aware that the model, the simple model, does not reflect the actual behavior of the ferrite bead. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.